So our next speaker for today is Paramanand Chandramouli. His talk is going to be about a bit too much, high-speed imaging from sparse photon counts. This is joint work between the University of Siegen and EPFL, and the authors are Paramanand Chandramouli, Samuel Buri, Claudio Bruscini, Eduardo Charbon, and Andreas Kolb.
Thank you, Ashok, for the introduction. Um, I would start with a brief preview of what we achieved. And on the top of it, you can see, like this is what we take as an input. So our input is such a video with just one bit measurement. So each pixel is either a 1 or a 0. And the scene is of an oscilloscope in which a sinusoid is being traversed. And from this sort of an input, we reconstruct something shown below. We try to maintain the same frame rate. So the input is at 156 kiloframes per second, and we try to reconstruct at the same frame rate. And one could also average these frames, but then you would lose the speed. So we don't see the transient effect of the traversing sinusoid. So we lose the temporal information. So this is just a glimpse of what we do in this work. And some details about the sensor. We have shown results with a SPAD camera. It stands for single photon avalanche diode camera. And today we saw, earlier in the previous session, we saw applications with transient imaging using SPAD camera. And we have seen many other applications in the computational photography with SPAD camera. The camera which we are using is known as Swiss SPAD, which features a large array, 512 by 128, and each pixel has a 1-bit counter. So you can just store in the pixel either a 1 or a 0. And we can achieve, the sensors achieve a global gating of about 5 nanoseconds. And to read out one frame, it takes about 6.4 microseconds. So that is where we get the 156 kiloframes per second. So inverse of 6.4 microsecond is 156 kiloframes per second. And we can also accumulate the bit measurements to get a higher bit depth image. And for those who are interested, I request you to visit the SwissPad 2 demo at ICCP during the demo session. So, and here is an example of the kind of images we get. The scene was of a resolution chart, and at 1 bit we see it's too noisy to make out any structure, and as we increase the number of frames, we see better. A B-bit image has 2 to the power B minus 1 frames. So 2-bit has 3, and 4 has 15, and so on. And here we also see there are some saturated pixels. These are referred to as hot pixels due to sensor imperfections. So just to state the objective, we want to overcome the trade-off between speed and quality. And we take a low bit high-speed sequence as an input and reconstruct a high bit estimate at the same frame rate. And just to clarify, currently we are not dealing with the transient kind of readings. So we just use it as a 2D, high-speed 2D camera. So in this work, we have not addressed the transient imaging aspect. So one could probably think of applying standard video denoising methods. There are popular methods called for video denoising, which work well for Gaussian or Poisson distributions. And most of these methods, what they try to do is they try to first combine pixels based on some criteria, either pick pixels that are close by or pick pixels which have similar intensity. And there are some priors or prior knowledge which is assumed to solve the denoising problem. But as you can see, such prior knowledge would not be useful in such a scenario. Like even if you have a gray level, a constant gray level, the reading would be something like this. And in such a case, imposing any prior constraints would not make much of a sense. There is also another line of work called as quanta imaging, which basically does a similar, which addresses a similar task, that is to reconstruct clean images from binary observed data. And even there, they first, in those methods, what they do is first they generate a slightly better image by averaging few frames, or they it's mainly similar to image denoising or video denoising methods. So they also need multiple observations to estimate one frame. So whereas in our case, what we want to do is we want to reconstruct the 3D sequence as a whole. So what we do is we take the 3D data, the spatiotemporal volume as the input, and our idea is to train a convolutional neural network which generates a clean spatiotemporal volume. And we intend that the convolutional kernels are trained in such a way that they combine the spatiotemporal information without, say, blurring, or we train an end-to-end network which kind of automatically learns how to combine information across frames. And for each bit depth scenario, we train a separate network because the statistics vary if we change the bit depth. And some more details about the data set we use for training. Currently, we don't have any data set for SPAD cameras. So what we do is we simulate data. And for the case of 1-bit and 2-bit images, which have a high speed, we also assume that there is high temporal coherence. So we use a video deblurring data set, which was captured with a high-speed camera. I mean, this data set is 720 frames per second. So we use this data set and we convert it to SPAD images, which I discussed subsequently, and then we train the network. And for the case of 3-bit and 4-bit imaging, we saw that we don't need a high-speed data set. We can work with normal video data sets, which are 30 frames per second, and still it works well. So just some more closer details about the image formation process. The photon arrival is considered to be a Poisson distribution. The number of photons arrive per unit time detected or also arriving and also getting detected can be modeled using Poisson distribution, considering the dark counts and all the other factors. And the parameter chi denotes the expected value of photon counts. And from this distribution, we can arrive at the probability of getting a 1 at a pixel. Like in the Sparse sensors, we get a reading 1 if at least 1 photon is detected. So we just have to plug in k varying from 1 to infinity, and we get this formula. So, and chi is kind of proportional to the scene radiance and many other factors such as photon detection efficiency and the dark count and all these factors. So, but what we are interested is in the scene radiance. So we see that the scene radiance gets mapped in a nonlinear fashion by this particular term at the sensors. So we see some sort of a nonlinear sensing of the scene radiance. And at the end, the image reading is nothing but a Bernoulli sample according to this particular probability. So we simulate images only through as a Bernoulli sample. And what we do is we we use the standard designs. Like image restoration has been around for a few years through deep learning, and residual network type of architectures have been applied for this problem with significant success. So we follow a similar approach, and yeah, I mean, this diagram describes our architecture. We have 3 residual units, and we train with the input 3D spatiotemporal patch and the true spatiotemporal patch with loss functions. And each residual unit has 3D convolutional filters. And we come to the results. So this are some samples from the synthetic data set. So if you look at the 1-bit observations, it's difficult to make out any structure. And the second column shows our reconstruction, and the third column shows the ground truth. So even in challenging situations, the network is able to perform quite well. And this is a real example of a milling tool which is rotating. And yeah, we see most of the scene is moving. Yeah, and we see the reconstruction is quite realistic. For comparison, what we did was we averaged 15 frames. So our input is somewhat cleaner. But when we applied a 4-bit reconstruction scheme, we see since the input is already blurred, we see a blurry reconstruction. And yeah, we have some, I mean, in the paper, we have many more quantitative evaluation of all the networks. And yeah, here I'm just discussing about the 1-bit example. So we have tried with different parameters, like different number of convolutional units and different number of residual units. So we pick the optimal value. And another aspect is like we change the downsampling unit. That is, as I mentioned, the data set, we take the deep learning data set and we downsample to create training and test data sets. So if we change the downsampling factor, that is, if we increase the motion, we see that the performance degrades. So this is so we study how much we can achieve. So here we in the top row, the motion is about 2 pixels per frame, and here it was about 4 pixels per frame. So up to 2 pixels per frame, when we tested the method on a large data set, synthetic data set, we saw that we can achieve a SSIM measure of about 0.7. So we can handle roughly 2 pixels per frame as motion. And as we go to 2 bits, then we can do slightly better with the extent of motion and also in terms of quality. And here we show with comparison with a true bit, like this was with 16 bits. We also see the hot pixels here, but our estimate is with just 2 bits, just 3 frames, and we do fairly okay. And yeah, this is for the oscilloscope 2-bit example where yeah, we see slightly improved with respect to 1 bit. And here we see different denoising methods, and the other standard video denoising methods do not work for 1-bit and 2-bit cases. We tested extensively with different parameters, and we found that the standard video denoising methods are not capable to handle those extreme scenarios. Whereas for 4-bit or 3-bit scenarios, the video denoising methods do generate reasonably good results. But we also see some sort of wobbling effect, like we don't see, for example, oh, sorry. Sorry for the caption, missing caption, but this is our result, and here you can see some sort of a wobbling effect by other denoising methods. And, yeah, in this sequence, we wanted to compare the performance of 1-bit, 2-bit, and 3-bit cases. So on the left, you have 1-bit, here it's 2-bit, and here it is 3-bit. And we dropped frames here. So they are all showing the same content. So for 1-bit and 2-bit, we have dropped frames. And still we see good quality reconstructions. We see slightly some sort of a blurry effects in 1-bit and 2-bit, whereas with 3-bit, it's quite good. So to summarize, this is yet another success story of convolutional neural networks. So we see that with 3D convolutions, we can reconstruct highly noisy data. And even though we trained with only synthetic data, we found it to be working on real data. For 4-bit, we have also shown, we have also captured a data set with sorry, we have a test data with, we have a real test data set. So there we have also trained with 4 real data and tested with real data. And we see like good performance. And yeah, so just to future directions, like we have currently some sort of a fixed architecture, like wherein we don't explicitly link with motion. So one could probably think of linking motion information and the spatiotemporal averaging or convolutional information to adapt according to whether it's a static or a dynamic part. And another possible direction would be to extend this for transient imaging or 3D time of flight calculations. So thank you for your attention.
Thanks. We have time for a couple of questions. So I'll give you all a warm start. I know that you model the input layer as a Poisson statistics and so on, but then eventually the convolutional neural network was trained using binary images as input as opposed to deriving some Poisson statistics, some lambda parameter for each pixel or something that actually utilizes the Poisson nature of the arrival time events. So do you have is there a particular reason for choosing that, or do you think that there is, it's worth thinking about incorporating the Poisson statistics directly within your network?
Yeah, in this problem, were just interested in 2D imaging. Like, in the gating time of 5 nanoseconds, we don't care at which time instant the photon arrived. So for this, we thought this was enough. Like, as just a Bernoulli sample, it would have been enough. So maybe if we try to do transient imaging, then those things become more important.
Okay. Any other?
I'm wondering how does it work in low light situation, like where read noise is also significant. Yeah, read noise.
Yeah, in this sensor we don't have read noise because it's just a 1-bit. The sensor itself has a 1-bit counter, so there is no read noise in this sensor. But yeah, it would be interesting to address. But maybe we should train it.
Are the detections happening asynchronously at the individual pixels, or is it all somehow synchronous?
There is some small jitter across pixels, so in the sensor.
So the arrival times of photons at different pixels are not really taken into account.
No, in this work we have not taken into account.
But I mean, do they exist?
It's in this. I mean, we can measure it by making multiple measurements with different fine shifts. But and they also have they are different at different pixels, and we were trying to calibrate, and it can be done. Yeah.
Thanks. One final question.
Thank you. So this is a scene-based method, and I'm wondering what is the performance on different lighting scenarios? For example, the bright scenes and the low light scenes. Can the same network generalize to different scenes? And the second question is, how about how much motion movement can you handle?
Yeah. Regarding the second question, about 2 pixels. I mean, for the 1-bit case, we saw that like if the motion is 2 pixels per frame, we could get reasonably okay reconstructions. And for low light, we have not really tested, but I mean, if for a real case, it also depends on the photon detection efficiency of the sensor and things like how many photons were detected in that particular lighting. So what in our experiments, we just use the normal lighting. We did not use any high illuminations, which is used in high-speed imaging. So it was just a normal lighting which we used. But it has to be a DC light. We can't, because it will capture the fine variations.
Thanks, Paramanand.